The student's t distribution. An important theorem called the central limit theorem states that the means from the sufficiently large samples drawn from a population follow a normal distribution. Hence, the properties of the normal distribution can be used to make predictions from the samples. Meaning to say, we can predict or estimate population parameters such as population mean and population standard deviation using sample statistics such as sample standard deviation and sample mean. When the sample size n is less than 30, the population standard deviation is not known, we can use student's t distribution to estimate the values of the population parameters such as the population mean. So meaning to say, if t-score is given and the test statistics are given, such as n is given with less than 30, sample mean is given, and then sample standard deviation is given, we can predict population parameters or estimate their values. Student's t distribution, or just t distribution, is a continuous probability distribution used to calculate population parameters when the sample size is small or n is less than 30, and when the population standard deviation is unknown. It was developed by the English statistician William Seeley Gossett under the pseudonym Student. That's why this is called Student's t distribution. Let's have this term, degrees of freedom. This is the number of independent observations in a given data set. So the degrees of freedom is just the number of samples minus 1, or n minus 1. Now, as the degrees of freedom or sample size increases, the t distribution becomes more similar to a normal distribution. That is why z distribution or standard normal distribution is used when the sample size is at least 30. So if it is less than 30, we will be using t distribution. If it is at least 30, we will be using z distribution. So let's see the graph, the difference of the graphs of t distribution and z distribution. So this one, the green one, is an example of z distribution when n is smaller than 30. When n is closer to 30, that's the graph, the red one. And if it is more than 30, it's close to, it's the z distribution already. So we'll be using z distribution if the number of samples is at least 30. For each sample of size n is less than 30 that can be drawn from the population, the sample mean obtained can be converted to t-score. So again, sample mean to t-score, and this is the formula. T-score is equal to the mean or sample mean minus the population mean over standard deviation sample divided by square root of n. Example number 1. Find the t-score for a sample of size 16 taken from a population with mean 10 when the sample mean is 12 and the sample standard deviation is 1.5. Take note that n is equal to 16, which is less than 30. Therefore, we will be using t distribution. So n is equal to 16, mu is equal to 10, or the population mean is equal to 10. The sample mean is 12. Sample standard deviation is 1.5. Now, using this formula, from sample mean to t-score, we have this. T-score is equal to 5.33. So meaning to say, if the sample mean is 12, the t-score is 5.33. Aside from the t-score formula, values for t-scores can be obtained from tables for t distributions with the given degrees of freedom, df, for the row names. So when we say df, it's actually the number of independent observations in a given data set. So these are the DF, or the degrees of freedom, the row names here. And level of significance, alpha, for the column header. So these are the levels of significance. So when you say level of significance, it is actually the probability that the event could have occurred by chance. So if the significance level is quite low, the probability of occurring by chance is quite small. We say that the event is significant. So that is the level of significance. Now T with alpha and degrees of freedom is called the critical values of T. So these are called the critical values of T. When we say critical values, these are the values that define the boundary of the level of significance. One-tailed tests allow for the possibility of an effect in one direction only. So either right tail or left tail. Now two-tailed tests test for the possibility of an effect in two directions, positive and negative. So this is an example of a two-tailed test graph. So two-tailed meaning to say, if alpha is given, we need to divide that by 2. So let's say, for example, if alpha is 1, we need to divide that by 2, such that this one is 0.5 and the other one is 0.5 as well. Because we are focusing on two tails, the left tail and the right tail. Now this one here, 1 minus alpha, is called the confidence level. So this one, the unshaded part, no? That's 1 minus alpha. It's called the confidence level. What does that mean? It refers to the percentage of probability or certainty that the confidence interval would contain the true population parameter when you draw a random sample many times. Okay, so that's the meaning of confidence level. So again, this one is the significance level, that one, and this one is the confidence level. So for one-tailed test, there are two types. We have right-tailed test and then the left-tailed test. So either of the two will be using this one here, one tail, level of significance, 0.5, 0.25, 0.2, and so on and so forth. So here in this example, you have 0.05. So this one is 0.05. That's our alpha, or level of significance. So our level of significance is 0.05. Our n is 15, meaning the degrees of freedom is n minus 1, which is 14. So we need to find 14. And then 0.05, the intersection is 1.761. So that's 1.761. Because it is right-tailed, so the graph is this one, the shaded part is this. And the area of that shaded part is 0.05. Same thing with the left tail. So the area of this shaded part is 0.05 as well. And the t-score is negative 1.76131 because it's on the left side of the graph. Example number 2, determine the t-scores in which alpha is equal to 20% or 0.2 using a two-tailed test when samples of size 10 are taken from the population. So take note, two-tailed test. Let's have the solution. So this is the graph. So we need to divide alpha because it's two-tailed. We need to divide that by 2. So 0.2 divided by 2 is equal to 0.1 or 0.10. So this one here is 0.10. That's the left tail, and this one here is 0.10. That's the right tail. So these are the level of, or the levels of significance. And this is the confidence level. That's 1 minus 2 times 0.10, because there are 2.10. So 1 minus 2 times 0.10 is 0.80 or 80%. That's the confidence level. Now we need to find this t-score. This one, the negative and the positive. That's why it says here, determine the t-scores. So there are two t-scores, the negative and the positive. Next, for the degrees of freedom, we have df is equal to n minus 1. Since n is equal to 10, so n minus 1 is equal to 9. So degrees of freedom, 9. And then two-tailed, 0.2. One-tailed is 0.10. The intersection is 1.383. So that's the t-score. That's the t-score if alpha is 0.2 and the degrees of freedom is 9. So t-score is equal to 1.383. Then after that, because there are two t-scores and the graph is symmetric, so we have 1.383 for the right side and then negative 1.383 on the left side. So there are two t-scores. Example number 3. A random sample of size 16 taken from a normal population whose mean is 25 is found to have a mean of 24 and a standard deviation of 3. Find the probability that a random sample of size 16 will have a mean of at least 24. So n is equal to 16 and it's less than 30, therefore we'll be using t-distribution. Population mean is 25, sample mean is 24, and sample standard deviation is 3. Using the population, the sample mean of 24 can be converted to a t-score of negative 1.33. So again, the sample mean of 24 is equivalent to t-score of negative 1.33. Because we need to find the probability that a random sample of size 16 will have a mean of at least 24, we wish to find the probability of t is greater than or equal to negative 1.33. So in this graph, we need to find this shaded part. And that shaded part is greater than or equal to 1.33. So we need to find that. But the t-table doesn't show the exact probability for t is equal to 1.33. So we need to find t is equal to 1.33 if the degrees of freedom is 15. So take a look at this. Degrees of freedom is 15 and there is no 1.33. Therefore, we will be using t-distribution function in Microsoft Excel. Now, steps in doing that. Steps in getting the desired cumulative probability using Microsoft Excel. We have number 1, open Microsoft Excel and choose one cell, any cell. And then number 2, type equals and then or equal sign tdist.rt. This one is the example, and then parentheses negative 1.33 comma 15. So this negative 1.33 is for the t-score and then 15 for the degrees of freedom, and then close and then hit enter. tdist.rt stands for t-distribution right tail, and then negative 1.33 15 is for the t-score and degrees of freedom. So an example of that is this. And then after hitting enter, the value is 0.898306. This shows that about 89.83%. So this one is 0.8983. So that's the probability that t is greater than or equal to negative 1.33. This shows that about 89.83% of all random samples of size 16 from the population will have a mean of at least 24.